All right, so if you have questions on the homework, we may have time at the end to entertain those questions, but I would encourage you to come by my office. I've already had 2 students come and visit. Lewis and Chris have come by, so they've already earned the bonus points that I offered on the first day. But here's the sign-in sheet for it. If you don't know today what you'd like to sign up for, you don't have to do it today. I'll bring this to class for the next week or so, all right? But it gives you some options for Monday, Wednesday, the time slots. Just kind of put your name there. I know it's real small. And if you can't do Monday, Wednesday, there's Tuesday, Thursday. So once the box is filled out, that time slot's taken, all right? So I'll pass this around. Like I said, if you don't know right now, then just pass it around and fill it out later. And then what else? So everyone was here last time and had an opportunity to do one of these sticks? Not missing anyone? Okay. All right, so we are going to start a new section today. And just reminding you that, again, today is a review. So I know if you did your homework, it brought up some things from the past, and there were some things that you may have not seen before. Hopefully you got help, or you come by and talk with me. Today, this section 1.2, I'm going to go very quickly through this, and then we're going to get right into 1.3, and that's where the course like begins, really. Okay, that's where the calculus starts. So this is really just kind of us running through like the Rolodex of functions that we should be familiar with. All right, so hopefully you can see this over here. These are our power functions, x raised to a positive integer. So x to the first, x to the second, third, fourth. So we all know the standard parabola x squared, x cubed. The only difference is left side goes down, right side goes up. And then the fourth power, you know, looks like the parabola, but not quite, right? It's kind of got tighter turn down here, and it grows faster. So just be aware of power functions and their general behaviors, right? Even powers, like this, right? Odd powers, like that. Okay, negative power functions. This is x to the negative 1, x to the negative 2. So we can always rewrite those as 1 over x squared, 1 over x cubed. And these actually qualify as rational functions. They all have a problem at 0. They all have an asymptote at 0, vertical asymptote, because these functions are undefined at 0. So there's 1 over x squared. Sometimes you'll hear me call this the volcano function. It just kind of looks like a volcano a little bit. 1 over x cubed kind of looks like 1 over x. So that's 1 over x in red and 1 over x cubed in green. Yeah, you get the idea, yes? Yes. Okay. Root functions. So the square root of x is only defined on non-negative numbers. So you cannot plug a negative number to the square root function. So it's going to look like almost like a parabola, right? It's kind of like laying on its side and they cut half of it off. Yeah? It's like you're taking the left side of a parabola almost and just like laying it down. So there's your square root function. So the domain of this would be what? What would be the domain of the root function? If I were to write it in interval notation, how would I write the domain of that? 0 to infinity. Okay, how about with your parentheses and stuff? How would that go? Closed on the 0 and then open on the parenthesis always. So that would be the domain of the square root function. You are allowed to plug 0 in, right? So when I do cube root next, is it going to have the same domain restrictions? Yes. Yeah. The cube root? Well, there's the picture of it, right? There's the picture of the cube root function. See, you can take a cube root of a negative number, right? The cube root of negative 8 would be, what would the cube root of negative 8 be? Cube root of negative 8 would be negative 2, because you can go negative 2 times itself 3 times would give you negative 8. So it's okay to plug negative numbers into the cube root function, and therefore the domain of the cube root function would be what? For this one? Everything, right? All real numbers? So we could do that with like negative infinity to infinity. You can also use that to represent all real numbers, or you can actually write down like all real numbers. It's up to you. Okay, what about the fourth root? Fourth root. Are we going to have domain problems? Yes, you cannot take the fourth root of a negative number. So anytime you have an even root, your domain is going to go from 0 to infinity. Anytime you have an odd root, cube root, fifth root, seventh root, ninth root, you can always plug in negative numbers. So there's your fifth root function there. All right? Questions, comments, concerns, complaints, gripes, nothing? All right, moving along. Polynomial functions. So you study these in Math 1414, college algebra, and you learn a lot about polynomials. You spend a lot of time here. And what you learn is that polynomials all have like the same sort of format. It's a bunch of terms with x raised to positive integer powers. So like a parabola is a polynomial, right? A parabola? Yes? Here's an example of a degree 1 polynomial. All degree 1 polynomials are lines. That means the highest power of x you see is 1. So this would be any line that you could pretty much think of that contains the variable x in it. And of course we can move lines around, right? We can try to move where they are. Here's the actual function we're looking at, x plus 3, right? So it has a y-intercept of 3, has a slope of 1. We can change the slope, right? We can kind of pitch the line. But the general idea here is that all lines are polynomial functions. And then we can go to degree 2. Degree 2 would be your parabolas, right? And of course you can have 2 x-intercepts, or you could have, how many x-intercepts? If you have a parabola, what are the possibilities in terms of x-intercepts? You could have 2. Can you have 3? Can't have 3. You could have 2. You could have none. That would be if the parabola is like above the x-axis. And you can also have just 1, right? What would it be if we had just 1? It would look like that, right? It would have to touch the x-axis at one point. But again, the idea here is that a polynomial function is just a bunch of terms where you have x, you have a highest power, and then the powers, decrease if we write it in that order. And then we start to get to higher order ones, like maybe we have like a third degree polynomial. And that's where we had to start talking about left behavior and right behavior. Do you all remember that? Like the left hand behavior versus the right hand behavior and what's happening. There was like a test you could run. Yes? I mean, I'm not sure. How is this? How's it going? Okay, now can I ask, was anyone not here last time? No? Okay. Now, is this like, am I speaking like Russian up here? Left hand behavior, right hand behavior for polynomials? How we determine that? Come on, this is your brain that needs the information. So. Do you remember when you were studying polynomial functions talking about left-hand behavior and right-hand behavior and how to determine what the left and right sides of the polynomial function will do just by looking at the function?
Whether it's negative?
Whether or not the left side is going to go down or up, that's down, sorry, down or up, whether or not the right side is going to go down or up. No? Doesn't sound familiar? Okay, so look, can you all see this okay? This is the function we're looking at. Just by looking at this, I can tell you that the left side goes down, the right side goes up. The way I can tell that is, first, it's an odd power degree. Odd means it's either going to do this or that, okay? Now, because the leading coefficient is 1, it's a positive number, that means it's going to do this. If that leading coefficient was negative, it would actually flip and go like that. And in fact, I will show you that. I'm going to change the leading coefficient to a negative number. Just look at the graph. See the graph? See it flip over? Okay. So that is the effect of changing the leading coefficient. So I'm not going to go back and and like teach this. I just want to kind of bring this up. This was called the leading coefficient test for polynomials. We could have, let's see, the shape. Let's change the shape of this thing a little bit. There we go. So look at this one, x cubed minus x squared minus 12x. There's the graph of that polynomial. In college algebra, what you were able to do is determine what the x-intercepts were. And I believe you even went in college algebra and tried to graph this. I hope you did. You should have. Tried to graph this. And when you graphed it, the one thing that we kind of waved our hands at, like kind of said, hey, we won't worry about that right now, was trying to figure out where it had its lowest point and where it had its highest point. Like we knew that there was a hump here, but we actually didn't know exactly how high it went. We could plug in some test points and try and get an idea, but we could never nail down the exact highest point and lowest point. Do y'all agree with me on that? There's no way to do it in college algebra unless you're dealing with a parabola. Okay, if you have a parabola, you could always find the lowest point and you could always find the highest point. Do y'all remember how? There was a formula. It was called the Vertex Formula. And it was a formula that you used in order to actually find that highest and lowest point. But after we went past parabolas into third degree, fourth degree, fifth degree, all we were looking for was end behavior, x-intercepts, and then we just kind of said, this stuff. Did your teacher tell you anything about these points? No? I always tell my students, we'll do that in calculus, okay? And we will. That'll be one of our main goals in this class, is if somebody gives us a polynomial function, we want to be able to find the highest and lowest points on that function. But to do it is going to require calculus, all right? But in order to work on these functions and try and analyze them, we've got to kind of have an idea of what they look like, which is why you graph them in college algebra. Okay, we could keep going. Fourth degree, fifth degree. Here's a sixth degree polynomial. You know, they look like roller coasters, right? These things look like roller coasters. And then you moved on, and you did rational functions. And rational functions were just a disaster, wasn't it? Like you could have all these vertical asymptotes, slant asymptotes, all this crazy stuff. And to graph one of these usually required a lot of work. So this is where, here's the function here. You have like a polynomial divided by a polynomial, then you'd have to factor, you'd have to check for holes, all this stuff, and then you go through this procedure. So let's just look at a couple of these. You know, I'll just kind of change them up, see how the picture changes. You know, see how that picture changed there? You know, just all depends on how I want to change the function. If I make little changes here, it makes huge changes in the graph. So we have vertical asymptotes, horizontal asymptotes, a bunch of stuff, x-intercepts. And then you took pre-cal. And you learned how to graph the sine function. There's your sine curve. Sine curve is periodic, right? Every 2 pi, but you can change the period depending on how you manipulate the function. So there's your sine curve, right? Here's your cosine curve. What's the domain of the sine curve? What's the domain? Is there anything you can't plug into the sine function? Like if I asked you to do sine of negative 3042, you could? Yes. Yeah, right? If I ask you to plug in sine of pi, you could, right? There's no number you can't plug in. So the domain of sine is everything. In other words, this graph continues in both directions forever, right? So the domain is all real numbers. I think some of you thought I was asking what the period was. The period is how long it takes for it to start repeating itself, and that's 2 pi. So cosine also has no domain restrictions. It's defined on all real numbers. Looks a lot like sine, right? It's really kind of just like a phase shift of sine just moved over. Of half a pi. Mm-hmm. All right, now tangent, that's where things start to become a little bit weird, right? Because tangent does not have an unrestricted domain. Tangent has asymptotes. And I'm going to take sine and cosine out of here. That's your tangent function. Remember that? Okay, it's like it's periodic. Okay, it does repeat itself, and the period, the length of the period is pi, but you have all these vertical asymptotes when you graph it. So what is the definition of tangent? In terms of sine and cosine, tangent can be rewritten how? Tangent x is the same as sine x over cosine x, right? So if you look at it this way, the only time you're going to have problems is if cosine is 0, right? If cosine is 0, you have a problem. So if we were to actually graph cosine again, notice that all your vertical asymptotes for tangent coincide with the x-intercepts of cosine. And in fact, that's the way that you can graph a lot of these reciprocal functions is by graphing sine, cosine. Yes?
When in calculus do we start using tangent is equal to 1 over, I think cotangent is equal to 1 over tangent, when you start using that?
When, I'm not quite sure there's a place that we'll use that, but there may be a problem where we're working with cotangent and we want to replace it with 1 over tangent, or the other way, because it's easier to work with tangent than it is to work with cotangent. I mean,
okay. I know in pre-cal,
mm-hmm.
anytime we use tangent or cotangent, it was either just sine or cosine or cosine.
That's usually when we were trying to like prove identities or do something. We always got it to sine and cosine just because it was easier to work with, right? Here, it's not so much going to be that. We're not going to be proving identities. So we're just going to be looking at a problem and saying, okay, if it has cotangent in it, do we want to mess with that, or would we like to change it to 1 over tangent? Yeah. Stay tuned. Yeah. Okay, so there were your basic 6 trig functions, and then we had all the reciprocal ones, right? Cosecant had a bunch of asymptotes also, right? And then secant also. And then cotangent, you know, they're all there. So these are all somewhere in your memory bank, filed deep, deep away in the cracks of your short-term memory, right? Gone.
Well, one method that you can use to make it easier for figuring out your asymptotes of secant and cosecant is just that secant is always going to be over a sine or a cosine wave, and cosecant is always going to be.
Yeah, we went to graph secant, you usually graph a cosine wave and then just use the points as like where these little things happen. Yeah.
Click on the sine and cosine.
Yeah, that's what I was kind of saying with the tangent function. Sorry, cosine, there we go. Yeah, so this lowest point on secant corresponds with the highest point on the cosine function. All right, so we have all those. I mean, like somewhere now on your formula sheets that you're allowed to have for the class, I believe there are graphs of the 6 trig functions on there, the basic graphs. And you're allowed to use those on a test, so just be aware of that.
And do you provide those, or do you
I do not. I provide them on Canvas, but I do not provide them like in class to you. All right, then there's exponential and logs. All right, so this is e to the x, one of our favorite functions. And in college algebra, you don't really, and in pre-cal, you really don't get to learn why this function is so great. But we'll talk about why this function is so great in this class. All right, just not yet. So that's e to the x. Exponential functions, all exponential functions look like this. That's what an exponential function looks like. And this is always a number, and we call that the what? The what of the exponential function? No? It's not a coefficient because it's not a times x. It's a raised to the x. So this is the exponent, right? This is called the base, right? So this is the base of the exponential function. And what we have for exponential functions is that a must be greater than 0, and a can't be 1. So as long as the number you put here is positive and not 1, then you're looking at an exponential function. And this is what they look like. Now this is e to the x, and e is a number, right? What is it approximately, e? E is approximately what number? No? I mean, we all familiar with the idea that pi is approximately 3.1415, right? Okay, but what's No? It's about 2.718-ish. All right, that's what E is. So E is a number, right? It's positive, and it's bigger than 1. And so whenever this base right here is bigger than 1, you have what we call exponential growth. This way, it goes off to infinity. In this way, it's a horizontal asymptote. It flattens out towards the y-axis. So if I graph here next to this 2 to the x, it should look very similar because 2 is bigger than 1. So it's going to be exponential growth also. When do I get exponential decay? When will it go this way? When this number here is what? It can't be negative. Less than 1, but still positive. So if you use like 1/2 raised to the x, that's the next one I'm going to look at. 1/2 to the x, that's the graph. So now it grows as you go out this way, but it decays as you come this way. Flattens out to 0. Okay, and then after you do all the exponential functions, you look at the log functions. So let me get some of these out of here. There's e to the x. Here is the natural log of x. And what is the relationship between e to the x and natural log of x? What's the relationship between those two functions? They are intimately related to one another. They are reflections over that diagonal line. That's called the identity. So if you look at that, tilt your head, they are reflections. And whenever you have a reflection like that over the identity, then those two functions are what of one another? No? Inverse. I don't know what you said. If you said that, good. Inverses, inverse functions. An inverse function undoes a function, right? So if you have a function, let's just say like the x squared function. Take something, squares it. The inverse function is the square root function and takes it back. So one of them squares, the other one square roots. Those are inverses. E to the x and natural log of x are inverses, which is why you have this property, again from college algebra, that when you put natural log and e to the x composed together like that, they kill each other off and you just get x. So these are all, yeah. Okay, let's look at a couple of other log functions. Oh, you know what we didn't talk about? The domains. I'm sorry. E to the x, 2 to the x, 1/2 to the x. All those other ones that I graphed earlier, what's the domain of all those? What's the domain of those functions? You just have to look at the graph. Does it exist? Is there anywhere where we don't have graph? Like, is there a graph this way forever? Is there a graph that way forever? For all of them? Yeah, all real numbers, right? So the domain of an exponential function is all real numbers. Now, what about the range? We've not talked about the range. But what's the range of an exponential function? So what comes out of it? You're looking at the y-coordinates now. So do you ever get negatives out? No. Do you ever get 0 out? Your graph never hits 0. Do you get positive numbers out? Yes. So whenever you have a function that's exponential, the domain of it is all real numbers, and the range is going to be from 0 to infinity. You only get positive numbers out. Now, what about all these log functions? There's natural log, there's log base 2, there's log base. Look at that. I even had a place I could have put the identity up there. I didn't realize I did that. Okay. So those are all log functions right there. What can you tell me about the domain of this, of all of these? Domain. 0 to infinity, right? And then what's the range? All real numbers. It's these two flipped over, aren't they? Isn't it flipped over? That's not a coincidence. When you have inverse functions, their domains and ranges switch places, right? Okay, I'm continuing, all right? What the heck is that? Did I scroll? Did I accidentally scroll? I didn't. Okay. Yeah. Okay, so look. Whenever we're learning all the different functions in college algebra and pre-cal, at some point you start talking about moving the functions around. So it's kind of like you learn how to draw a basic one, and then you learn, okay, I can move it up and down and left and right, and I can flip it over and reflect it. These are all the different things that we can do. If you add a number to it, it moves the graph up. If you subtract a number, it moves it down. If you add a number inside the function, it moves it not that way, right? It moves opposite of what you think. And then this right here, if you subtract a number inside the function, it moves it to the right. So these are all translations or transformations of graphs. And this works for any function. If you know what that looks like, then doing this to those functions just moves it around. And then you have your stretching. So you can read this on your own, go back, review college algebra. But stretching, you put a number in front, and it's either going to stretch it this way or stretch it that way, depending on the number. And if you make the number in front negative, it's going to reflect over the x-axis. If you put the negative in the function, it's going to reflect over the y-axis. So you have translations up, down, left, right. You have stretches vertically and horizontally, and you have reflections. And these are all the algebraic steps, or the things you'd have to do to the function algebraically to make it happen. I understand this is like I'm recapping like a lot of stuff here in like this amount of time. Don't get overwhelmed, all right? It's just, these are things that we need to have somewhere within our heads. Somewhere in there we need to be able to go back and reference this and not take 3 hours to go do it. Is that a question?
Yes. These reference notes, these are on camera?
Yes. Now you can't interact with them like this. Okay. Yeah. So this is an example. This is an example of a parabola, and then we can do some translations and shifting and reflecting and move it around. Yeah. Here's same thing with sine. You can take like a sine function and change the amplitude and phase shift and period, all that stuff. Okay, and then in college algebra, we also talk about how we combine functions together. So this is actually worth us thinking a little bit about, because functions are kind of a special creature. When you're learning arithmetic in grade school, you're learning how to add numbers, subtract numbers, multiply numbers, divide numbers, right? Those are the only operations that we have. There's 4 of them. You can do those 4 operations on numbers. Those are the only operations you can do. Do you agree with that? What about exponents? I didn't include that. I said add, subtract, multiply, divide. What about exponents? Exponents is just multiplication. That's all it is, right? 3 to the 4th power is 3 times 3 times 3 times 3. So that's covered in here. So if you take 2 functions, right, you can add them together. If you have 2 functions, you can subtract them. If you have 2 functions, you can multiply them. You have 2 functions, you can divide them. Those are the arithmetic operations of functions. But with functions, there's another thing you can do, a 5th thing that you can't do with numbers, and that is composition. So you all remember that, f of g of x? So when you see that symbol f of g of x, what that means is you're going to take the g function and plug it into the f function, right? If you switch this order, that means you're going to go, the f function goes into the g function. And it's composition as opposed to multiplication or division or addition and subtraction. So I thought we would do this example here, but I'm not quite sure I want to do all of those examples because I think some of those are pretty straightforward. So let's just take that. I give you 2 functions there, all right? What is this? What is that equal to? So what is that telling you need to do? Multiply the 2 functions together, right? So all that means is you take the f function, multiply it times the g function, and then multiply those 2 together. So when you multiply things like this together, it's called expanding. So we are going to expand this. So here to here, here to here, here to here, and here to here. So what do we get here? X cubed minus x to the fourth. Please, not all at one time, please. Raise your hand if you want. Minus x squared, right? Okay, and then collect all your like terms, and we don't have like terms, do we? So that's it. Now, is it okay for me to leave it like that? You can rearrange it, but that is, I mean, technically that's correct. Now, a lot of times we like to write our polynomials in descending order, highest power of x down, but that in no way makes it more correct, all right? They're both equally correct. All right, so that's multiplication of functions. Now, what about this? So what I'm going to do here is I'm going to take the f function, but inside of it I'm going to put what? The g function. Which really means I'm going to take the f function and plug in g. What's g? X minus x squared. So now what I'll do is I'll take x minus x squared, plug that into the f function. So I'm going to replace that x with that entire quantity. Then plus 1, yes. So I'm going to do x minus x squared squared plus 1. So that's f of g of x. Are there questions on that? I think we've had time to warm up. Okay, what about this? What's the difference here? Yeah, it's backwards, right? This time you're going to go g, and inside of g you're going to put what? F of x. So that really means you're going to take g, and inside of it you're going to plug x squared plus 1. And that x squared plus 1 is going to go in for this and that, right? Both of those are going to become x squared plus 1s. So x squared plus 1 minus the quantity x squared plus 1 squared. Are these two functions the same? No, not, and they don't ever have to be the same. All right? Does anybody know what we could say? Let's say that I gave you two functions, okay? And let's say we did f of g of x, and let's say at the end we got x. And then I asked you to do g of f of x of the same two, and you also got x. Does anyone know what you could then tell me about those two functions? They're not the same functions. Not, well, I don't think like is the word we would use for it. Maybe I can help you this way. What does it mean to say that f of g of x would turn out to be x? That means when you plug x into g, you get an answer, right? Then that function, that answer then goes into f, and f spits back x, the same thing you plugged in. And then when you do it backwards and go x into f and then all of that into g, it spits x back out also. Haven't those functions basically undone one another? So they are inverses. In fact, in college algebra, if you took an appropriate college algebra, the way to prove that two functions are inverses of one another is to show that f of g of x is equal to x and that g of f of x is equal to x. If you can show those two things, you've shown they're inverses. Okay. Let's continue with this. What is g of f of x? You got it, sir. Go ahead. You got the table. No?
Are you looking at inverse?
No, no, him.
Yeah.
Yes, sir. Should I move on? Okay, wake up, please. That should have costed you 10 points on your next exam, right? Didn't I talk about that, sleeping in here? I don't like sleeping. It's a big pet peeve of mine. All right, unless I wake you up and you can tell me exactly what I'm supposed to do, then I don't care if you sleep all day, okay? What's g of f, oops, sorry, g of f of x. G of f of x. Now you don't normally see this in college algebra because they like to stick to the Fogg and Goff thing, but there's nothing that says that we can't take x, plug it into f, take that answer, plug it back into f, take that answer, and then plug it into g. You can have, in theory, you could have a string of compositions that's 20 compositions long. So this would mean g inside that is f, and then what's inside of this f right here? F of x, which is x squared plus 1, right? Then what? This goes into f, right? So it goes right there. So that becomes, we still have g out here waiting to take its turn. But what's the, let's see, I'm going to start calling you out. Chris, where's Chris? Oh yeah, Chris, you're the Chris. You know what, you're off the hook. You came in to visit my office today. Chaz.
Chase.
Chase, that's right.
It's pronounced Chase. It's the Latin.
That's right, because there's a bar on that.
Yeah.
But I'm not an English major, so I just know that the bar means something. Okay.
It means repeating. You know math.
Okay.
Just call me.
So I should just go cha, che. Okay.
Whatever.
All right. So what would go in here now?
It would go g, and then wherever the x's of g are, you would put the f of f.
Okay. So what is this? Tell me what that is. What is f of x squared plus 1?
Like the technical term? Or
No. Just it's algebraically it's something. It's an expression. What is that expression?
x squared plus 1
Okay.
plus, and then you square that,
Okay. Good.
and then you plus 1.
There you go. So that is plugging this in for that x and then squaring it and adding 1. So we've done, this in here is f of f. And then now we have to take that answer and plug it into g. So who gets that? Tatum? Where's Tatum? Tatum, you're up. So basically this, right?
Yeah.
Okay, so you want me to write that down first? Okay. So that is getting plugged into this thing, right? So I think you're just referring to that piece right there now, right? Okay, so keep going. Minus. Yeah, I'm going to do big parentheses for you.
X squared.
This thing?
Yes.
And the plus 1?
Squared.
Squared. There you go. That's g of f of x. That's g of f of f. I can't say it. G of f of x. That's a triple composition. Yes?
So when you're doing these, it's easier to work from right to left.
You have to work right from left. Yes, when you see this, you're working this way. X goes into f, that answer goes into f, that answer goes into g. All right. Not bad, not bad. Let's keep going.
Would you want us to leave that like that, or
Well,
expand it out?
oh yeah, no, leave that. In fact, what we just did there is more of an exercise to make you think about, there's more that, a lot of times in college algebra, students are just shown f of g of x and g of f of x. And so they think like those are the only ways you can compose functions. You can have a chain of functions put together, maybe 5 compositions. It's where we're headed, okay? All right, so here's some more compositions. I'm not going to do it. This one's the big one right here. We are not so interested in doing what I just asked you to do. We're actually more interested in going backwards. That means if I were to give you a final function, capital M of x is sine to the fifth of x squared plus 1, can you actually find three functions that, when composed together, would give you that? Okay, so let me see if I can't make this make sense. We have to come up with three functions right now. F of x, g of x, and h of x. We need to find those three functions so that if I asked you to compose them, f of g of h of x, that when you were done with that composition, you would get that. Does that make sense?
Yeah.
Okay, now before I do it, I have some questions about capital M for you. Is it anise?
Yeah.
I say that right?
Anise.
Anise. Okay.
spelled weird.
Okay. I'll do my best. Anise. Okay.
I go by Nas. I go by Nas.
Nas. Okay. Let's do that instead. Nas. Okay, Nas.
Yeah.
My question, this is going to be kind of a weird question, but let's say that I asked you to plug a number into that for x. What would be the last operation that you do? And if you don't understand the question, I can try and clarify. What would be the last operation you do?
Is sine to the 5
Mm-hmm.
the whole thing, right?
What are you asking?
Sine to the fifth of the whole
So you're
squared plus 1, right?
You're verifying with me, and I think you're confirming with me that that fifth power actually means sine x squared plus 1. It's actually like all of that to the fifth power.
Yes.
That is correct. And that's what I want to make sure everybody understands here. When you see this exponent here, what that really means is you would have to do the sine first, then you would raise it to the fifth power. All right? So in terms of order of operations, I was asking Nas, if I asked you to plug in a number, you would plug in, let's say you plug in 2, okay? You would square the 2 first, right? Get 4. You would add 1, get 5. You would then take sine of that, you get your calculator out, sine of 5, and after you do that, you would then raise it to the fifth power, right? That would be the order in which you do things. Y'all agree?
Yeah.
Okay, that's it. Good.
Okay, good.
That's it. You're good.
I think you kind of know the answer.
You want to keep going?
I mean,
You think?
maybe, yeah.
Okay.
I think f of x is going to be is x to the 5.
Okay.
Am I right?
I'm not going to tell you until you're done.
Okay. And then g of x could be sine of x.
Okay.
And then h of x is going to be x squared plus 1.
That is correct. Okay, let's see if we're all on board with that. So I asked Nas, originally asked him what would be the last thing that happens. And he confirmed that it would be the fifth power would be the last thing that happens, right? And I asked that really because I want to make sure everyone understood that notation really means this. But when we're trying to come up with the functions that will do the composition, when you have f of g of h of x, the last function, the last one is f, right? The one before that's g, the one before that's h. So when you're trying to figure out what f is, what you have to do over here is think to yourself, what's the last operation happening? The last thing that's happening is I'm taking something here and raising it to the fifth power, right? So let's say I'm taking x and raising it to the fifth power. Understand? Now, we need to go find h. We've already taken care of the 5, haven't we? So if I look at what's left in here and I say, okay, what's the next function in? Or in other words, the second to the last thing we would have done. Didn't we say we would take sine next? So I'm going to be taking sine of something. So why don't I make my g function sine of something? Does that make sense? Sine of x. So now we've done the sine. And now we're left with one more thing inside. And well, that is just x squared plus 1. So let's just leave it and just say that's our h function. Y'all got that? So it's kind of like I worked my way from the outside in, like an onion, like a layer. We had the fifth power sine and then the inside of the sine. By the way, what's this thing inside a function called? The thing that you plug inside of a function. Does anyone know the name for that? No? Okay, it's called the argument of the function. Okay, so the argument of the sine function here is x squared plus 1. All right, I want to challenge us. Can somebody come up with something else that does the same thing? This might be hard.
So you would have the same answer but going in different order?
Well, I'm saying you'll get capital M still. When you're done doing composition, you'll get capital M, but it won't be the same F, G, and H. Well, they won't all be identical. Let me, because of time, let me see if you believe this. Would that work? So if I told you to do composition of this, first thing that would happen is H would go into this, right? So if I take x squared and plug it in right there, what would I get? Sine of x squared plus 1, right? And then I take that and I plug it in right there, and what would I have? Sine of x squared plus 1 to the fifth power. Do you see how that creates the same thing, that composition?
So what you're saying is multiple answers?
They're not unique. That's right. There's not a unique decomposition. If somebody gives you a function that is a composition of functions, there may not be a unique one, a unique decomposition. However, there is one that makes the most sense to us, and this is the one I think that makes the most sense to us. This one, yes, it could be done, but I don't think it's as clean as this one is. What kind of follow that? Okay. Let me give you another one, and then we're going to move on. How about this one? Capital M of x equals the square root of the natural log of x plus 1 squared. All right. So here's what I want. I want you to find an f, a g, an h, and a k such that capital M of x is f of g of h of k of x. So can you break that down into the composition of 4 functions? Right, that's the question. I'm going to give you a second to think about it, and then I'm going to pull a stick here, and someone's not going to be happy. The good news is that if I've called you, you won't be called again unless I get through this entire stack. The bad news is if you haven't been called, it's going to happen at some point. Remember, I'm not trying to embarrass you. I'm not trying to put you on the spot, make you all nervous, all right, hurt your feelings. I just find that when I do this, people just seem to want to pay attention a little more. All right, here's what I'll do. I'm going to call 2, and then we'll see if one of these 2 are ready. Savannah and Derek. And I think I'll try and help y'all unless you have something yet. Savannah, do you have any? Savannah? I can't hear you, Savannah. There you go. Believe it. Believe it. You know it's right. Huh?
You want me to like write it?
No, I just want you to say it. You said it like, kind of like, I think it's the square root. It's the square root of, yeah, go with it, right? Go with it. Square root of x. Derek, do you agree?
Yeah.
Do you understand
Yeah.
that? That's the last thing that happened. Yes.
How do you know that's?
So how do you know it's the last thing that happened? Great question. Think about, again, if I asked you to plug a number in for x, let's go through the order of the way things would happen. Here, replace that with a number. What's the first thing you would do? So if I said put 2 here, what would you now do? Would you? Yeah, would you? Does that make sense? You would add the 1. Okay, now what would be the next thing you would do? You would square it. What would the next thing do? So now you got something sitting here, right? Now what you would do? You would take the natural log. It's not multiplication, but you would take the natural log. And then the last thing you would do would square root. That's what we're doing. But we're working backwards now. So square root, Derek, you're up because Savannah already got one.
All right, can I start like from the bottom or go start at G?
I don't care where you want to start from at this point.
K is going to be x plus 1.
You want to go x plus 1? You want to keep going?
And then for h, it's going to be natural log of x.
I think you're grabbing too much at one time here. You could do natural log of something here, but then this one you wouldn't need this one. So go through what Savannah was saying. First thing that would happen would be you'd put these together, right? And then what's the next operation after that? Squaring, right? So why don't we just put x squared here? And then now, Savannah, it's back to you. ln x. Yeah, ln x. So imagine, you have to kind of like see if you can put this puzzle together in your mind. This thing goes in here and becomes x plus 1 in parentheses squared, right? Then that goes into here. So now that's natural log of x plus 1 squared. And then all of that gets put into here, so you get the square root of all that. Okay. That's it. We're moving on. Now, I told you that 1.2 was supposed to be review. What we just did is not review. I don't think anyone did decompositions of functions in college algebra or pre-cal. We will get more practice. The limit of a function. So if you go and you look at any textbook that has calculus in it, you can look at the limit as being like the heart of the topic, of the entire subject of calculus. From the idea of this thing called the limit, it branches out to everything that you do in a calculus book. In fact, differential equations branches out from here. Everything is based upon this idea, all right? It's one thing, and this is where we started. And we're going to start by talking about what's called the limit of a function. And when we do this, it's going to be very visual. There's going to be a lot of things to look at here. And so if you're having trouble, you're going to need to let me know. Like, I just don't see it. So I'm going to start just real quick, just throw that graph up there. Can everyone see that okay? We have the x-axis here. It's kind of an orange. The y-axis is here. I put these dotted lines here to kind of help you see where the points are. And what I'm interested in right now is asking you a question that requires no calculus at all, and that is asking you the question, what is f of 2? So this is the function f. I've drawn the graph for you. If I'm asking you what f of 2 is, then what is it that you need to do? Don't help. Karen's going to tell me. Karen, where's Karen? Hi, Karen. So when I say f of 2, do you have some concept of what you should do by looking at this graph to figure out what f of 2 is? Okay, go for it. 8. So Karen, you should go 8. You know, like y'all should be, just go for it. No one's going to care, right? Is anyone going to walk out of here and be like, Karen, this Karen character in my class? She said 7. I mean, come on. Who cares? Just say it, you know, confident. You're right. Okay, that's correct. F of 2 means when you go out to 2, right? What point corresponds to that? The y-axis you go up, right? Figure out what that value is. It's 8. Very straightforward. And that is college algebra. So essentially, here's what's happening. When I ask you what f of 2 is, I'm asking you to ignore the entire graph and just concern yourself with what's happening at 2 on the function. Nothing else in the graph matters. Do you agree with that? Yes? Yes. Okay. Just wanting to know what's happening at a specific point on the graph. Now, I have another question. What is happening to the function as I approach 2 from the left-hand side? So let me try and visualize. We'll visualize this. Imagine you are moving along the graph like on a roller coaster. Okay, and you see yourself coming in here. Notice the x-coordinate is getting closer to 2, right? And then you have your y-coordinate. Right now it's about 4-ish, right? So as I get closer and closer to 2, from the left-hand side, what does it appear the y value is approaching? What does it look like it's getting closer to? Looks like it's getting closer to 8, doesn't it? I'm going to get even closer. Right now we're at 1.99, and our y value is 7.9598. It's getting closer to 8, isn't it? And then let me get even closer. Oh, wrong one. Oops. Got too many things here. So now we're at 1.99, which is even closer to 2, and I'm at 7.996. So I think just from the picture, it looks like as I come in this way, getting closer to 2, my y value gets closer to 8. Yes? Does the same thing happen if I come in from the right-hand side? Let's see. So what happens? Let's take a look. That's our x-coordinate right there. There's our y-coordinate. Do y'all see the y-coordinate? It's 8.46 right now, right? So it actually got bigger than 8. But that's OK, because what's going to happen? It's going to go up. But then as I get closer and closer to 2, it's going to start coming back down towards 8, right? So this is the idea behind the limit. We are not doing this. We are not looking at the function at a point. We're doing the opposite of that. We are ignoring what the function is doing at the point. We are completely ignoring this, and we are just concerned with what happens as we get close to there. All right? Do y'all see the huge distinct difference between those two ideas? Okay, let's do another one. So it appears that now if you scroll back up, I have that pretty much summarized. From the left, the function's value appears to be approaching 8. From the right, the function's value appears to be approaching 8. At 2, the function's value is 8. And that's what, I'm sorry, Karen, right? That's what Karen told us, right? So everything that we are looking at on this graph had to do with what's happening at 2. Yes?
And now, is that important? By being important as in like knowing how it approaches from both left and right side? Is that important when determining the asymptotes?
We're going to, yeah, we'll look at something where we have asymptotes. Let's get to that, yeah. But for now, let's start with another function, and let's see the difference here. So now I've given you a piecewise function. I'm still interested in what's happening at 2. And I had to pick a number, so I'm just going to stick with 2 for a while, all right? So here's a different function. Is it a function, first of all? Is it a function? Does it pass the vertical